Thank you. Okay. ಬರಕ್ಕಾಗಲ್ಲ ಕೊಡ್ತಾ ಇದ್ದೀನಿ. Thank you. Thanks, sir.
Okay, so good evening and welcome back. Concluding day 2 of the STEM's final camp, I'm honored to introduce Dr. Bangalore S. Sathyaprakash, an exponent in the field of gravitational physics and cosmology. He obtained his PhD from the prestigious Indian Institute of Science, Bangalore in 1987. Having authored and co-authored hundreds of research items, his research interests include sources of gravitational waves and their detection, cosmology, large-scale structure, classified field theory, symmetry breaking, and many more. He is currently the Burt Elfbach Professor and the Professor of Astronomy and Astrophysics at the Pennsylvania State University and the Associate Director of the Institute of Gravitation and the Cosmos, and is also the member of the Gravitational Exploration Institute. He is also a member of the coveted LIGO Governing Council since 1998. Throughout his illustrious career, Professor Sathyaprakash has held various positions in institutes all over the world, including the International Center for Theoretical Physics in Tri-State, Italy, the Inter-University Center for Astronomy and Astrophysics, IUCAA Pune, etc., and has given dozens of talks at various international conferences. Today, he'll talk to us about black hole collisions, something which we have forever wondered about at some point in our childhood. So without any further ado, over to you, Dr. Sathyaprakash.
Thank you very much for the invitation and that very nice introduction. I hope everybody is doing well in this extremely difficult time for everyone. And coming to this lecture on a Saturday evening really means a lot to me. I hope I'm able to convey to you the excitement of this research. It is a research that is carried out by hundreds of scientists around the world. And what is important in this effort is the involvement of students and postdocs and even undergraduate ones throughout the world do take part, and it is their untiring effort that really helps us in doing this research. So kudos to students all over the world. So let me now start sharing my screen. If you have any questions at any one point, I don't mind at all if you ask questions. Somebody should watch the raise hand or any questions in the chat. Just let me know and I'll be happy to answer. Okay, let's start sharing the screen. I assume that you are able to see my screen. So I'm going to talk about black hole collisions, really, which are the most powerful explosions in the universe. You all learn about black holes or hear about black holes, but normally somebody would say black holes are black. You can't see them. You can't get any radiation from them. That is true if black holes are in isolation. There is nothing else around them. However, the moment you put some matter around them, or if you put another black hole near it, black holes become immediately the most powerful explosions. And I'll try to argue what that is in the following 30, 40, 50 minutes. Okay, we have to start with Newton's idea of space and time to begin with, to appreciate what I'm going to talk about today. According to Newton, space is absolute, and he said it is in its own nature without relation to anything external. That means it just exists there. You cannot modify it, you cannot touch it and deform it. It just stays there and you can't do anything. And about time, he said absolute time in and in of itself and of its own nature without reference to anything external, it flows. It flows uniformly, and you can't change it. You can't modify it. Those were the concepts that Newton believed in, even though um, he really did not expect uh, that space should change. It's remarkable. Nobody thought that one should explicitly make that statement. And that's because, in order to formulate his mechanics, he had to imagine things moving in space. And if space itself keeps changing, then it becomes problematic. So he had to explicitly state it. But it's really, I find those statements remarkable. Who would think that the space time around you would change? You have to make that assumption. Anyway, there he is, imagining that space time consists of some very rigid structure, and then clocks that are placed in this rigid structure are all the clocks are running uniformly, no matter where in space they are, whether they are close to Earth or Sun or a black hole, they would all flow at the same rate. So that's the way he thought. And in particular, if there are particles and matter, time is not affected. Space is not affected by the geometry.
Sorry to interrupt. Are you changing slides? It's still on the title slide if you are.
Oh, goodness. I'm surprised. Why does it not change?
Yeah, now it's changed.
I know, but when I go to full screen, it doesn't seem to change. So I need to figure out just a minute. What about now?
Yeah, now we see the picture. Could you just try changing slides so that this?
No, but it's not changing when I press button.
No, we still see Newton thought matter does not affect.
I have no idea why this has happened today. Maybe I should stop sharing just a minute and share it. But the problem is, if I go to its full screen mode, I cannot.
Even without this full screen mode, it's very readable. So
I know, but there'll be things that won't look nice. So this has now become. Now, what about now? Are you able to see the screen change? Okay, I think I have to share the entire. Okay, this is what I was talking about earlier, that Newton thought that space is a rigid structure. There are clocks, and these clocks simply don't, the rate at which they flow, it doesn't change. This is what he thought. But then came Einstein along some 200 years later, and he noticed, really as a result of some ingenious experiments, two things. So you should be able to see Einstein's picture on the left, and there is a little girl sitting on a rocket, shining a torch, holding a torch in her hand, and speeding away from the lady standing and watching her. And it turns out that both the lady who is standing on the ground and this little girl will measure the same speed for the speed of light. This is actually remarkable, because one would imagine if the girl is sitting on a rocket and shining the torch, the speed of light as measured by the lady on the ground should be the sum of the speeds of the rocket plus the speed of light relative to the girl. So that should be what it is. But it turns out that experiments that were carried out in late 1800 showed otherwise. This goes by the name of Michelson-Morley experiment. They were trying to really do something else, but this remarkable result is what came out. Anyway, one consequence of the speed of light being the same for all in relative motion is the following. You all know that Einstein's most famous equation E equal to mc square. I'll show you another one which physicists love of Einstein's equation. For them, it is not really this that is famous, but another one. And the second consequence is that there is something called time dilation or twin paradox, which results in twin paradox. What does it mean? If you have twin brothers, one of whom goes on a rocket for a few years and comes back, the person who went on a rocket and came back seems to have aged less than his twin brother who decided to stay on Earth. And this is called the twin paradox, and it is something that we observe on a day-to-day basis when particles that decay, that are fast traveling, right, on the Earth's atmosphere, if they are fast traveling, depending on their energy, therefore, they seem to have different decay times. Um, that is the reason for that is really this time dilation. The faster they travel, the longer they live, is what we watch. But the third consequence is something also remarkable, which is that nothing can travel faster than light. If nothing can travel faster than light, then it turns out one has to rethink how Newton's gravity works. And that's what I'm going to talk about. The other thing that Einstein um, had already known is something called precession of perihelion of Mercury. So the diagram on the right shows you the orbit of Mercury, highly exaggerated, around the sun. It's on a slightly elliptic orbit. And as it goes around, it turns out that the point of closest approach, what is called perihelion, itself keeps on shifting in course of time. Itself goes around. And Newtonian gravity, in fact, already predicts, because in addition to the force of sun, the Jupiter, which is the second heaviest body in the solar system, also tugs at Mercury. And this causes Mercury's orbit to precess. And people knew about this, astronomers, and they had predicted something like 532 arc seconds per century. So it's an extremely tiny effect. What you see in the picture is highly exaggerated. But the observed shift in the position of that perihelion means the point of closest approach. The observed shift is something like 575 arc seconds per century, and this is a discrepancy of about 43 arc seconds per century. Extremely tiny effect. It was measured. Remember, 1 arc second is only 3,000th of a degree, 3,600th of a degree. Given how small an effect this is, one might immediately think, oh, maybe there is some experimental or measurement error. People who are making measurements, they made an error. But a few decades before, people, Verrier in France, had actually predicted that the motion of Uranus, and in particular Uranus, meant that there must be a planet outside the orbit of Uranus, which is affecting its orbit. And lo and behold, they discovered Neptune this way. So Newtonian gravity has been extremely successful in astronomy and in predicting even the position of Neptune. So in this case, they thought that there was an orbit, there was a planet inside the orbit of Mercury, and they even gave a name to it. They called it Vulcan, and they tried to find, and they thought that there may be an additional tug, which is very close to Sun, so we cannot see it. Even Mercury, we can hardly observe it except if you are up in the morning or late in the evening, depending on the position of Mercury. However, if it is too close, then maybe you won't see it. But they made a lot of attempt to very careful observations, including during the eclipse, but nothing was found, which meant that the discrepancy remained, and Einstein knew about this discrepancy. It turns out, it's a long story. It turns out that because of universality of gravitation, one cannot think of gravity as a force, but it is actually, it changes the curvature of space and time around massive objects. This is the only way he could reconcile the two things that I mentioned. One, if you have massive bodies, then you really cannot expect the space-time to remain rigid. It changes. Both space as well as time will change. Let me explain to you what curvature of space actually means. Suppose you have a body like Earth. This is only a schematic. The change in the curvature is actually in 3 dimensions, but let me try to use this schematic. It's not as if Earth is sitting on some grid and and there is some gravity that is doing it. It's just that Earth is sitting in space, and you imagine measuring distances between objects. Suppose you measure distance between A and B, which are separated by a certain number of grid points, you get some value. And if you measure the distance between C and D, where you pass very close to Earth, you measure a different value. Okay? They are separated by the same number of grids, but obviously, if the space is curved, you would get a larger value for the distance between C and D than A and B. This is the meaning of curvature, but it happens actually in 3 dimensions. That's why this other figure is more appropriate if you want to describe. It is changing in all dimensions. So, but this illustration is easier if you write it in 2 dimensions. Now, what is the meaning of curved time? Curved time means if you are close to a very massive body, like the black hole on the right, then you are likely to have your clock run slowly compared to a clock that is close to Earth, which is not so compact an object. So in the case of the planet near this black hole, if you saw the movie Interstellar, the hero of that movie, he spends only a few hours on that planet, but that is equivalent to several years on Earth. And when he goes back and meets his daughter is older than him. So that effect is very nicely shown in the movie Interstellar. Okay, that's the meaning of curved time. It's not as if clocks, get bent or anything like that. It just means clocks run at different rates. Now, according to Einstein, therefore, you remember the picture that I wrote for space and time. In summary, then, according to Einstein, space-time is not rigid. Clocks run slower if they are close to a gravitating object like sun or black hole, and space also gets curved. And this has remarkable property and very well described by John Archibald Wheeler, and it is described by these equations. These are called Einstein's equations. You don't really need to know what this G alpha beta and T alpha beta are, but I'll tell you what they represent. But the important thing is just that it is multiplied by this so-called coupling constant 8 pi G divided by C to the 4th. So the left-hand side of this equation describes the geometry of space and time, and the right hand describes the matter distribution. So John Archibald Wheeler famously said, matter tells space-time how to curve, and space-time in turn tells matter how to move. And the coupling between those two is that number 8 pi G upon C to the 4th. I think I removed the slides describing that, but anyway, let me just describe to you a little bit more about what this really means. So if you have clocks, up there in satellites, Earth's satellites, going around artificial satellites, then there are two effects that you have to worry about.
Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day. Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds fast every day.
So this is an effect that is known. I hope you were able to hear the description. This is a real effect, and it is known, it has been measured, and it turns out if you don't take this into account, using your Google or your favorite app to navigate around a city would completely fail within just 10 minutes. You'll be off by more than 10 meters. So if you don't take this effect that Einstein is predicting, both for special and general relativity, that clocks get affected, you will be completely off course. So this is something that we know that really happens. But the other consequence, which is extremely profound, according to Einstein's theory, is that, well, we learned that gravity is responsible for bending of space and time. But what then prevents it from this bending of space and time to change as a function of time? So imagine that there are two stars, as in this picture, that are going around each other. Then their position is changing. Therefore, the ripples that are there on space and time, they keep changing as well. And those ripples will travel outwards, according to Einstein's theory, at the speed of light. And this is what we call gravitational waves. So gravitational waves are nothing but the changing curvature in space, but also time, that propagates as a function of time. So this is what gravitational waves are. And that is what Hulse and Taylor discovered indirectly. So in about 1976, two very famous scientists, Hulse and Taylor, shown here, found that in a binary consisting of two neutron stars, very tiny compact objects, only about 10 to 15 kilometer in size or radius, for an object that is 1.5 times as massive as the sun. One of them acts as a pulsar, is sending radio pulses towards us, and the other one we can't see in this picture. You can see them both, but the other one is dark. But using that pulsar that we can see using radio observations, we can very accurately time the orbit, and it turns out the orbit is decreasing. The orbital period is decreasing about 72 microseconds per year. It's again a very, very tiny effect, but one can make that measurement very accurately. And that is also in contradiction with Newton's gravity, because according to Newton's gravity, the orbit should remain stable forever. It should not become smaller and smaller. And this is what is happening. Eventually, these two neutron stars, after about 300 million years, will come close to each other and merge. And in that period, they will emit gravitational waves that are extremely powerful and we will be able to observe them. Of course, you don't want to wait 300 million years to make these observations. However, there must be other neutron star binaries in the universe, and if we can observe coalescing or merging or colliding neutron stars, we should be able to detect gravitational waves, right? That's the whole point. And in the almost for a long time, more than 5 to 6 decades, scientists have been trying to build instruments that can detect gravitational waves. The first one among them was Joe Weber. He more than anybody else, understood very clearly that gravitational waves stretch and squeeze space-time. They alter the rate at which clocks tick. And he made use of this in order to build a very simple detector called a bar detector already in the early 60s, and tried to detect gravitational waves by the oscillation of that bar, or a cylindrical bar, as gravitational waves go by. It turns out the sensitivity of his instrument was not good enough, but he is a pioneering scientist in our field, and he also thought about what are called laser interferometer antennas. The reason why he did not detect is that space-time is, as we discussed, is very rigid. It's not easy to deform it. In order to produce gravitational waves, you need very powerful sources. But how rigid is space-time compared to other things that we know? Rubber is easily deformable, for instance. You can easily squeeze it and deform it. And its elastic modulus, which is measured in gigapascals, is about 0.1. Wood, on the other hand, is also is easy to deform compared to metal like steel, and its elastic modulus is something like 10 GPa. Steel, diamond, you see all these objects which are extremely hard to deform, but you still have about 200 and 1200 in the two cases. But space-time is so rigid in the frequencies that we are going to talk about. It is 10 to the power of 24, extremely rigid, so much so that it is only takes catastrophic events to produce gravitational waves. To detect these gravitational waves, there are now instruments around the world, and I'm going to show a picture of each as we go along. This is what is called the LIGO Livingston Observatory. It is in the state of Louisiana in the US. It is in south eastern corner of United States. And there is LIGO Hanford Observatory, which is in northwest in the state of Washington, in a place called Hanford. And then there is the Virgo detector, which is located in a place called Cascina in Italy, close to Pisa. Virgo has 3-kilometer arms. It is a laser interferometer. As gravitational waves pass, they change the length of the arm as measured by an observer, and that is what allows us to measure gravitational waves. In the case of Virgo, it is 3-kilometer arm lengths, and in the case of LIGO, they are 4-kilometer. Both Livingston as well as Hanford, they are both 4-kilometer arms. Virgo is 3 kilometers, but larger the arm length, greater is the sensitivity. Up to a certain point, greater is the sensitivity for gravitational wave detectors. In addition to that, in Japan, there is a detector called Kagra in the Kamioka mines. It's an underground detector in order to shield the detector from ground vibrations. Japanese are already building what I would call the next generation observatory. Already, currently they are commissioning it. In addition to that, as you may have heard, there is plan to build a detector in India called Ligo India. This will also be a 4-kilometer one. Kagra is a 3-kilometer one. And Ligo India is a project that has been in principle approved by Indian government, but the construction should start sometime soon. I believe the buildings have begun to be constructed, but the detector, if it, finally, if it is allocated, should come in about 8 years, 8 to 10 years. Now, the field began by observing the collision of two black holes. Here is a video showing it. For some reason, seems to be a little slow on my screen. I don't know if it is working for you. The two black holes in a faraway galaxy, they came together and they merged. They lasted in our detector only for about 200 milliseconds. But in that period, we were able to observe it. That was the first observation of gravitational waves. It is called GW 150914 and it represents here 15 is 2015. That's the year. 09 is September, and 14th is the day. The 14th day of that month when we observe it. So you will see many numbers like this throughout the talk. And what it means is that there was a gravitational wave event that was observed in that particular day. Sometimes, in addition to this, there will be time mentioned, GPS time. But that's because there may be more than one event observed in that day, and you want to distinguish. So 150914 was the first detection of black hole binaries, first direct evidence for a black hole, first detection of gravitational waves. It was many in one discovery, honestly. And for this discovery, three of my colleagues, Rainer Weiss, Kip Thorne, and Barry Barish, were awarded the Nobel Prize for 2017. That was a really very fitting award, and it was a moment for celebration. I was part of this discovery because of some involvement that started more than 25 years ago. I designed algorithms to detect gravitational waves from merging black hole binaries. And when these black holes come together and merge, for a short while, when they are highly deformed because they came together and merged, they emit more energy in gravitational waves per unit time than all the stars in all the galaxies in the universe. Okay? Think about that. It outshines the entire universe in light, entire universe in light for just that one moment. Except that this radiation is not optical, it's not radio, it's gravitational waves. Now, there were certain already very puzzling things that during that discovery, the masses of black holes that were observed were far larger than anybody had imagined. And also, it turned out that the rate at which the black hole merge as compared to what astronomers were predicting was far larger. And one thought that maybe these black holes were actually produced not by evolution of stars, but in the very early universe, and they are called primordial black holes. Altogether, the first and second observing runs saw something like 10 binary black holes in total, and it's a population unlike what we know in astronomy. I'll show you one slide to describe what I mean by that, because the masses are far larger than the black hole masses observed in astronomy. In addition to these 10 binary black holes, the first of two observing runs, which concluded in 2017, in fact, at the end of August, the detectors were turned off to make further improvements. And on 17th of August 2017, saw the first detection of the collision of a pair of neutron stars. And this is a remarkable event, as I will show you in a minute. And it turns out that it is led to several firsts. Let's begin with what the observation is. On the top, you see the gamma ray observation. At the bottom screen here, bottom of the screen here, you will see gravitational wave observation. It is what we call just a time frequency trail on the bottom. So that's when the two neutron stars collided. And about 1.7 seconds later, we also had an excess in gamma ray observation. So let's listen to it again. Gravitational waves. And then gamma rays. Okay, 1.7 seconds later, a mere less than 2 seconds later, the Fermi Gamma Ray Observatory and the Integral observed the gamma rays. So this is remarkable. So what happens in this case is the two neutron stars have come together and they have collided. In the case of black holes, they will simply be more gravitational waves at that point. There's no other form of radiation. But in this case, what happens is that there are these neutron stars containing matter. They produce an extremely explosive ejecta, which leads to very complicated phenomena. And I'll describe some of them as we go along. So what LIGO and Virgo observatories were able to do is to locate the position of the source within about 28 square degrees. The final localization was 16 square degrees. And this allowed astronomers to point their telescope in that direction and discover a transient. Okay, on the right-hand side here, you see what the emission looks like on just a mere 5 days later, right? 17th is when gravitational waves were observed, gamma rays were observed just 2 seconds later. 5 days later, you see a transient here, which is fading extremely rapidly. So it's not a source that lives forever. So in the field of view predicted by LIGO and Virgo, astronomers were able to see a fast, rapidly fading source. And that fading source is produced by the collision of two neutron stars, and it occurs in near a galaxy called NGC 4993, which is about 120 million light years away from us, or 38 megaparsec in the units that astronomers use, or 120 million light years. So this collision happened, when the Earth was already pretty well developed with all the life, but 120 million years ago. Now, this is a great measurement because it allowed us to compare the speed at which gravitational waves travel and the speed of light, because both electromagnetic radiation in the form of gamma rays and gravitational waves arrived within 1.2 seconds. Sorry, 1.7 seconds or 2 seconds. Now, if you travel for a very long distance, and even if you have tiny difference in your speed over, if you travel over 120 million light years, even tiny difference, as much as a few parts in 10 to the 16, then that would lead to more than 1.7 seconds. Okay, because even if the difference in 1.7 seconds, as shown on the left-hand side here, would mean that the difference in speed is no more than a few parts in 10 to the 16. And this is a remarkable inference or measurement. And it turns out that many alternative theories of gravity proposed to explain what is called dark energy had to be thrown out because of this measurement. But most importantly, this is also something that affects our understanding of the periodic table, in the sense, where do these heavy elements come from? In the heavier elements such as gold, here there is zirconium, there is rhodium, rubidium, all these heavier elements, they cannot be produced in stars. stars can only cook up to maybe iron, but not beyond that. Now the question is, where do these elements heavier than iron come from? And it turns out there was a prediction: either they could be produced in supernova, or they could be produced in neutron star collisions. So when two neutron stars come and collide, I mean, neutron stars are simply a big ball of neutrons. And when they collide, there is a ejector that comes out. Most of the matter simply collapses, and it collapses to form a black hole. But the collision process leads to about 1/10 or 1/100th of solar mass being ejected. And these are extremely high velocity neutrons moving in some random directions, and they collide with each other and they form heavier and heavier elements by what is called OR process, and they produce heavier nuclei. Most of them decay, because if you make the nucleus heavier and heavier, it becomes unstable. And this decay product is what we are seeing. Basically, this is some sort of nuclear explosion, if you wish. That is what is producing this electromagnetic radiation. And it produces radiation in the entire electromagnetic spectrum: radio, microwave, infrared, right? Optical, UV, X-ray, gamma ray. The entire electromagnetic spectrum is filled by this R process production and the decay of the products. And so this really helped us solve the puzzle as to where heavy elements form. This was predicted already in the 70s, among others, by a colleague by name Jim Latimer. But this was confirmed by the observation of these things. It is one thing to predict, as long as it's not confirmed by experiment, it's not something that we can believe in. And this fireball is what is called kilonova. And you see an artist's picture. It's not a real photograph, but an artist's picture. The other one that I showed you here is real, but what you see in here is just an artist's picture. But it also provided a new tool for cosmology. Now we can measure distances very accurately. It turns out that gravitational wave observations can allow us to measure distances very accurately, which means that this observation allowed us to help measure the expansion rate of the universe using a completely different tool. We know that the universe is expanding already by observations by Hubble in the 1930s. And electromagnetic observations have been used to measure that over the years, especially supernovae have been used to measure the expansion rate of the universe. But here is a new tool, and this is important, as I will tell you later towards the end of the lecture. It turns out that there is a problem with the expansion rate. There seems to be a chat. What is it?
I'll voice the chat questions towards the end.
I'm sorry?
I'll voice the chat questions towards the end. That'll make it a bit easier.
Okay, all right, that's good. Yeah, keep them putting in the chat window. We can talk about it towards the end. In addition to that, this measurement helped us understand a little bit better the structure of neutron stars. I kept talking about neutron stars. It is true that most of the neutron stars contains just neutrons, no protons, not many electrons, not many protons, but mostly neutrons. As you know, neutrons are not fundamental particles. They are composed of what are called quarks. In this particular case, there are 3 quarks that come together and form a neutron. And it is true, most of the neutron star is made up of quarks. Sorry, made up of neutrons. However, neutrons, as I said, is made up of 2 down quarks and 1 up quark. It is suspected, and we don't know, that the core of this neutron star might actually be composed of either free quarks, as in the right-hand side here, and quark gluon plasma. That means, normally you can't make these three quarks in a neutron separate out. It is called confinement, quark confinement. But when the density is extremely large, when the pressures are extremely high, maybe they deconfine. And what the neutron star core consists of are what are called free quarks, including the strange quark, up quark, and down quark. Strange quark, it's because it's the most stable form of quark matter. If the neutron star, heavier neutron stars are really are composed of strange quark, then as shown in this diagram, they will be slightly smaller compared to neutron stars if they contain only neutrons. We don't know which one of this is true, but gravitational waves in future will be able to make observations of this. All right, now over the past about 1.5 years, LIGO had his what is called third observing run. It started in November 2018, but due to the pandemic, we had to shut down the observatories in 2019. Soon after, sometime around March, we had to shut it down. But during this observation, not 2020, sorry, March 2020, during this period, many observations were carried out, and I want to describe some of them, but here's a summary plot so far. We now have what is called the second gravitational wave transient catalog. The first catalog contained 10 binary black holes and one binary neutron star, but here now you have something like 45 binary black holes in this diagram. And then there are 2 binary neutron star observations. There may even be a neutron star black hole. But if you now compare the binary black holes observed by LIGO, the masses of the black holes which come together and merge seem to be predominantly larger than about 20 solar masses. There are some which are below 20 solar masses. And they are like the electromagnetic black holes observed in X-rays. And then the neutron stars probably have a maximum mass of something like 2.5 solar masses. And in between, there seems to be nothing, but merging binary black holes do produce objects in that mass gap. And I will talk about some of those things. So what are the properties? So there are 2 binary neutron star events. There are 44 confident binary black hole events, and one of them might be a black hole, binary black hole. That's why I was saying 45. But one of them could be a neutron star black hole. We don't know. The rate of mergers inferred from this is that it might be about 25 per year per gigaparsec cube. 1 gigaparsec is 1 billion parsec, and 1 parsec is about 3 times 10 to the 16 meters. So you can see this is a large volume, and so these things don't occur very often, but since our detectors can see far away, we are able to detect them. Whereas binary neutron stars, they merge at the rate of 320 per year per gigaparsec cube, about 10 times larger. I will not describe the other properties, and I will skip this slide, but I want to talk about some special events that were discovered during this phase. The first in my list is what is called GW190412, discovered on 2019, April 12th. Here, as the animation predicts, these are 2 black holes. The mass ratio is about 1:3, and the 2 black holes going around, one of them 8 solar masses, the other 30 solar mass, produce not only what is called the quadrupole radiation, but also higher harmonics, which were not observed until this system was detected. And it produced many more patterns and confirmed Einstein's theory. So that's one thing. The second in my list is 1904-25. In this case, the second object is probably a binary, a neutron star. Both the first and the second. It's the second binary neutron star observation after 1708-17. But this system was only about 3 to 4 times farther away than 1708-17. And because of that, and also because LIGO and Virgo could not tell exactly where in the sky the system is, astronomers could not observe the afterglow or the counterpart. So the reason why we say they are binary neutron stars is because of the masses that we infer for the companion objects. The origin of this system, nevertheless, is a challenge to astrophysics because the total mass of this system is unlike any system we have observed in the Milky Way. The galactic neutron stars, the total mass is far less compared to this system. So it's gravitational waves are already throwing challenge, but more to come. 1908-14 discovered 2 years after 1708-17. This 08-14 is really a mystery object because one of the objects is about 23.2 solar masses, and that is definitely a black hole. But the companion, which is 2.6 solar masses, has a mass that is larger than a neutron star that had been observed until now, any neutron star, but lighter than any black hole observed so far. As I said, astronomers believe that there is a gap in the maximum mass of a neutron star and the lightest black hole, and that is called the mass gap. And this object sits right, the companion here, sits right in that edge around 2.6 solar mass, and it's a mystery object. It may be the heaviest neutron star or the lightest black hole, or maybe completely something different, what are called boson stars or soliton stars. We don't know what it is, and future observations might be able to help us discover other sources. Maybe with improved detectors, we'll be able to conclude what they are. So it's a mystery object so far. But it doesn't stop there. We discovered another system on 21st of May, 2019. And in this case, the two black holes are shown on the poster on the left. One of them is 85 solar masses. The other is 66 solar masses. These black holes should not exist in the universe by stellar processes. If you evolve a star, no matter how massive it is, you may start with a star that is 100, 200, 500 solar mass. What will be left over, according to stellar evolution, is about 50 solar mass. You can't have anything more than that. But here is an object that is so heavy that we don't understand how it formed. Probably it is the product of earlier mergers of black holes that resulted in this 85 and 66, but we don't know. Again, more observations should tell us. Okay, that's really the end of the talk, but I want to tell you a little bit more about what is coming in the future. Currently, there is what we call crisis in physics. I won't explain each of these unless there are questions. What is called black hole information paradox. Information falls into a black hole, but it doesn't come out. And that's not good from quantum mechanics point of view. The center of a black hole has a singularity beyond which physics cannot be explained. And that is not good for general relativity. So far, there is still a lack of a viable quantum theory of gravity. And that's an embarrassment for physics and physicists, because all other forces we have been able to quantize except for gravity itself. Moreover, not only is the universe expanding, there seems to be an accelerated expansion of the universe. The only way that can happen is if there is something called mysterious dark energy, a vacuum energy, which is pushing the universe. It is the energy of the vacuum itself but it is a very peculiar property. It has property unlike any other matter. That's why it is called dark energy, which seems to be pushing. And the origin of dark energy and dark matter is complete mystery. The so-called Planck satellite a few years ago observed this picture for the microwave background on the sky. This is the entire sky. Some parts are cold, some parts are hot, but the difference is only a few hundred microkelvins. So don't think that this is very large, but it's a very precise measurement. And it also implies that our universe consists of normal matter, which is only 5%, the mysterious dark matter about 26%, but in addition to that, there should be dark energy about 70%. And we don't know what's the origin of this dark matter and dark energy. And finally, I mentioned to you about the Hubble constant. There seems to be two different ways to measure the expansion rate of the universe. And one of them gives a value that is around 69. The most important thing is the so-called Planck measurement here, which gives a value around 67 or so. Okay, 67.66 plus minus 0.42. But there are measurements by using supernova in the local universe that give you a value 73.24 plus minus 1.74. You see, this is a discrepancy at a level that cannot be understood as a measurement error. This is such a large discrepancy that it leads to what is called the Hubble tension or Hubble expansion tension. And finally, our universe seems to contain black holes everywhere. This is a picture of the Milky Way near the Hawaii Mauna Kea in Hawaii. When you observe the center of this Milky Way, it seems to contain a black hole around which stars seem to be swirling around. We don't see the black hole directly, but only the stars. This particular star here seems to be going around in a period of about 12 years or so, 10 to 15 years. And that seems to be going around something and which we don't see, and its mass inferred from the orbit of the star is about 4 million solar masses. The origin of these heavy supermassive black holes is also something that we don't know. The good news is that there will be new detectors both on ground and in space and in many different, observing in many different frequencies that will help us understand some of these problems. The reach of these new instruments will be the edge of the universe. We'll be able to observe nearby sources with stupendously bright signal to noise ratio, but we can observe them wherever they are. These many black holes and neutron stars, wherever they occur, we'll be able to observe them. We will be able to learn about phenomena that took place in the early universe. There's a long list of things, including phase transitions and so on. And finally, we can also address the question of whether the black holes that we observe came from the primordial universe or were they produced by stellar processes. So the future observatories will also address some of the founding questions or fundamental physics questions, such as the black hole information paradox, whether we need to change general relativity to avoid the singularity and infer the presence of dark matter and so on and so forth. So that's my concluding slide. Gravitational wave observations have already made massive discoveries, but the future really looks bright for gravitational wave observations with detectors that will be put in place, new detectors, both on ground and in space. With that, thank you very much for your attention. I'll be happy to take any questions that you have. Thank you.
Thank you very much. So that was indeed a beautifully structured session, starting off from right from the very basics of black holes and going on until what lies ahead in front of us and what is currently being researched. That was a wonderfully structured talk, along with like beautifully dispersed data and other images and videos, which mainly because of which you were able to capture the entire audience throughout. So thank you very much for that. So I'm sure there are plenty of questions in the chat. I already received quite a few.
Okay.
Please do put out, for the audience, please do put out the questions in the chat and I'll voice them over. Please refrain from unmuting yourselves. Um, Firstly, are the currently known properties of dark energy similar to the properties of once thought ether, which provided a medium for electromagnetic waves?
That's a good question. Probably, I mean, we didn't know, scientists really did not uh, explain in the 1800s what exactly the properties of ether were, except that they thought that in order for light to propagate, there must be a medium. Because in order for sound to propagate, sound cannot propagate in vacuum. So scientists thought that in order to propagate uh, light, you need a medium, and that was called ether. Nothing much more than that was exposed, except that it could not exert a drag on Earth. Otherwise, things like Earth would fall into Sun if there is a drag force. So it was called this omnipresent ether, but it has to be there in order to explain why light can travel from distant stars and so on. But nothing much was known. But there are what are called ether theories, which are similar in ideas to 1800s. But at the moment, we really don't know much about what dark energy is.
Thank you, sir. And there's one more question. To resolve Hubble's tension, can we not say that Hubble's constant depends on time?
Oh, it does depend on time. There's no doubt at all. In fact, the rate at which the universe expands is higher at earlier times. And we believe that probably it went through what is called accelerated expansion at the birth of the universe, and it's called inflation. However, that's not what we are talking about. We are talking about the rate at which it is expanding now, even though it is inferred using the cosmic microwave background radiation, those observations require a constant in front of them, which is the expansion rate now. And therefore, that is the tension. Yeah, absolutely. It changes, but the tension is about the current value of the expansion rate.
Okay, thank you. And Arnab, do you have a follow-up question for this? So do type it in the chat if you have any. And so then another question. So do gravitational wave detectors alone tell us about the location of the merger, or do we need the map of gamma ray bursts as well? If so, why not?
Wonderful question. It turns out that gravitational wave detectors are what are called quadrupole antennas. If you have a radio antenna, you only need to change its orientation a little bit. It doesn't matter where the radio station is, you will be able to receive signals. That is true with most radio antennas. Gravitational wave antennas, not all radio telescopes, by the way. Radio telescopes have extremely small beam size, but I'm talking about antennas that you put, like microwave antennas on top of the house and so on. But gravitational wave detectors can watch, especially the network, something like 60-70% of the sky all the time. The way we locate where the source is coming from is by what is called timing. It's exactly the way the GPS clocks up there are used to find where you are. The GPS clocks, we use a network of those GPS clocks. They detect where you are, and they send the signal to you. Here, a network, and that is done simply by timing, right? It is done by timing of the arrival times. Here, in the network of gravitational waves, depending on where the source is located, you will have different time delays with respect to the geocenter in the different detectors. And that timing will, allows us to locate the position, but not very well. It turns out in order to do that, you have to have a very long baseline to do very precisely. So our positional information is still pretty poor. As I said, something like a few tenths of square degrees. For 1708-17, it was something like 28 square degrees. But it was still better than the gamma ray. Gamma ray also cannot locate the source very well. And so astronomers had to make a tile and observe different parts within that tile and observe it. Observing telescopes really have very narrow beam width, and that's the reason why they can't observe the entire sky. They can only observe what is called a pencil beam at any one point. And gravitational waves helped locate where the source was, and that's how they could do follow-up observations.
That was a beautiful answer. Thank you very much, sir. And so this question is relating to something early on which you spoke about. The objects you mentioned while talking about elastic moduli, such as wood, diamond, etc., are physical objects. What about space-time? How do we calculate its elastic moduli?
Yeah, it really is something that comes directly from Einstein's equation. I will just go back to the Einstein's equation itself. I won't be able to fully explain unless somebody is interested. I can do the calculation. It takes a little bit of time, but it turns out you don't need to be a specialist in general relativity to do the calculation. But I don't know where I put the Einstein's equation.
And you'll have to share your screen.
Just a minute. Yeah, here it is. So here the Einstein equation. On the left-hand side is what is called the curvature, as I said. The right-hand side is what is called the stress tensor. It measures the stresses, whereas the left-hand side measures the strain in space, strain caused by the presence of matter. And the right-hand side is the pressure that is applied. So you have stress over strain, which is like c to the 4 upon g, but there are some other factors that come into play. And basically by that coupling constant tells you what is the elastic modulus of space-time, but it depends on frequency. The lower the frequency, it is easier to deform it. It is also true with materials, right? If you take a material, its elastic modulus depends on the frequency, and at audio frequency of ground-based detectors, it is 10 to the 24 gigapascal. But the space-based LISA detector, it will be about 6 orders of magnitude smaller. So it's easier to stretch and squeeze space-time at lower frequencies.
Okay, thank you. So that was interesting. And maybe the penultimate question: how do you describe the event horizon of a black hole mathematically? And is the singularity of a black hole like a hole in the space-time?
Very good question. Let me explain maybe by using a whiteboard. It's not going to be perfect, but the event horizon is described as the surface from which you cannot receive light rays. So let me draw here the picture of this is space and time. This is really X and Y, and here is a black hole. Actually, that is not X, it is T, time. This time. Now, if you are far away from the black hole and you emit a ray of light, either in the positive X direction, Y direction, or negative Y direction, they travel at the speed of light. Like here I'm using a unit where the speed of light is equal to 1. So light rays travel along the diagonal here. Okay. As I said, it's not going to be a great picture, but this is called the light cone, if you have observed it. As you get closer and closer to the black hole, so at far away, this angle here, that is pi by 4, 45 degrees. As you get closer to the black hole, the light would want to more and more fall into the black hole, so it gets deformed. It gets deformed such that it would be more like this. So it's harder for the light to get out. Okay, see the slope here, but it is easier for it to get in. The slope on one side is smaller than the other. Right near the horizon, it gets even more deformed. The light is now barely getting out. You can see this slope is even larger. And finally, when it comes to here, near the horizon, light cannot get out. Whatever you do, it simply is emitted. It's not, time is going there in that direction. It really stays put. That means time becomes frozen for somebody there, okay, just on the surface. But if you are inside, then in fact, space and time become intermingled. You cannot stay at the same point in space anymore. You have to move with the in the direction in which the light ray is going, and everything ends up at the center of the black hole. Now that is what is called singularity. And the question was, what was the question about singularity?
So the question was, is it like a hole in the space-time? Is
Yeah, hole
singularity
in
of a black
space.
hole
Yeah,
like a hole?
good. It is called a hole. The hole, including event horizon, it's called a hole because, yeah, it is a purely geometrical object. A black hole is, strictly speaking, there are some caveats. However, it's a hole in the sense that the space-time comes to an end at the singularity, right? And the physics, as we know, completely fails. So in that sense, the center of the black hole is where the space-time in a way ends, and we can't make any predictions. Already at the event horizon, it is a geometrical object. It doesn't allow light to. That's the reason why it is said that somebody passing through a black hole horizon will see the entire future in a flash. And some movies actually capture this as well. That is how we know what black holes are currently. Whether anything changes on the surface of a black hole due to quantum gravity, we still don't know. That's something that is unknown currently. Does that help?
Absolutely, that was a really lovely answer. So thank you for that. Uh, so maybe the final question. So what went behind figuring out the perihelion of the Mercury's precession?
It's just sheer focus and great effort. Telescopes are wonderful instruments. You can very precisely make measurement of position of Mercury. All it needed was a good old telescope, not the telescope of today. Today, telescopes are great. And these telescopes were able to, refracting telescopes in those days, were able to very precisely figure out where the position of Mercury is. That is all. That's all you need. Where is Mercury at any given time? Given the orbit of, for instance, Earth around Sun, or that of Mars around Sun, you know very precisely the mass of the Sun by orbiting other planets. And the distance of Mercury from the Sun is known. And from this, you can figure out exactly what the orbital motion of Mercury must be, and also because of the presence of Jupiter. That is all that was required, only positional information of Mercury to know this. Yeah.
Oh,
Again,
okay.
very good question, by the way. Yeah.
Thank you, sir. And yeah, Arunangshu has a question. Yeah, sure, you can unmute.
Sir, you were saying that when something is falling into a black hole at the event horizon, it will see the entire future of the universe in an instant. So from an outsider's perspective, can we say that even at a point of time in the future, the object is still not totally inside the black hole. It is still at the event horizon, and hence actually nothing is falling inside the black hole, but just staying at the event horizon.
This is the reason why I said, yeah, there are caveats in the sense that for an observer who is very, very far away, this is a wonderful question, by the way. You can never say the black hole has formed by stellar process. Some of the properties that I described is only true for what is called a black hole that has existed forever, which is not true. The universe started 13 billion years ago. A black hole has not existed forever, and therefore we cannot make some of the statements, some of these statements for the real black holes. So, but they are approximately true, almost true. But if you ask me in principle, has the black hole really formed from a star, and can an observer infer that? The answer is no, because as we discussed in that diagram, I don't know if the things would have gone. Yeah, okay, here. This light ray here, right? The light ray sent from here will reach the observer. The observer might be very far away, doesn't want to get close to the black hole, but it will reach at some point. Okay, this will also reach at some point. You know, it may take longer. This will also reach at some point, but this will never reach the observer, and therefore yeah, you're right. The observer at infinity will never observe the formation of a black hole. Wonderful question.
Thank you, sir.
Thank you, sir. I think with this, we can come to a formal close of the session. So once again, I request all of you to kindly join me in extending a hearty thanks to Dr. Sathyaprakash for this wonderfully and passionately delivered lecture with plenty of example-driven and very much statistical evidence, and it was overall a beautifully structured session. So thank you very much for this.
Thank you very much.
Thank you,
Have a
Professor, for
good day and
accepting
good
our
week.
invitation.
Sure. Thanks a lot. Take
Thank you,
care.
sir.
Bye-bye.
Thank you, sir. Have a good day. Bye.
Bye.
So, we now meet tomorrow at 9 a.m. When we have Dr. Rajiv Gandhi from Rutgers University talking about an invitation to algorithm design. So I really hope to see you all there, and hope you had a good day too, and will continue to have a final day as well. So thank you for joining, and bye-bye.